Welcome to my class of operating system. Today we will learn CPU scheduling, and under CPU scheduling we will learn FCFS. CPU scheduling, it is divided into preemptive and non-preemptive. But first of all, we need to understand what is the meaning of CPU scheduling. Since Windows is a multi-programming environment, so we need to take care, or we need to process different programs at the same time. That is, we need to schedule different processes. We can say that CPU scheduling is the basis of multi-programmed operating system. By switching the CPU among processes, the operating system can make the computer more productive. So here we will learn CPU scheduling concepts, and soon we will learn CPU scheduling algorithm. The first algorithm is FCFS algorithm. The rest of the algorithm we will do in next class. Earlier we have learned that on operating system that supports thread, it is kernel level thread, not processes that are in fact being scheduled by operating system. However, the term process scheduling and thread scheduling are often used interchangeably. They are used interchangeably. Now actually, what is meant by scheduling? Scheduling of processes of work is done to finish the work on time. Why do we need scheduling? A typical process involves both input output and CPU time. In a uniprogramming system like MS-DOS, time spent waiting for input output is wasted and CPU is free during this time. In multi-programming environment, one process can use CPU while another is waiting for input output. This is possible only with process scheduling. So this is the criteria, or so the requirement of the scheduling occurs. This is the, you can say that scheduling of resources, scheduling of CPU time, it is required. What is CPU scheduler? Earlier we have learned there are two types of scheduler: short-term scheduler and long-term scheduler. But let me explain. Whenever the CPU becomes idle, the operating system must select one of the processes in the ready queue to be executed. The selection process is carried out by short-term scheduler or CPU scheduler. The scheduler selects a process from the processes in memory. From a pool of processes, CPU scheduler select one process that are ready to execute and allocates the CPU to that process. So note that there are two types of scheduling. One is we call preemptive scheduling and another is non-preemptive scheduling, as shown in this slide. What is preemptive scheduling? CPU scheduling decisions may take place under the following four circumstances. What are the four circumstances? First circumstance, when a process switches from the running state to waiting state. For example, when a process switches from running state to waiting state, like for example as the result of an IO request or an invocation of wait for the termination of one of the child processes. When a process switches from the running state to the ready state, For example, when an interrupt occurs, a process changes its state from running state to ready state. Third one, when a process switches from waiting state to ready state. For example, at the completion of input output. And what is fourth one? When a process terminates. So these are the four circumstances when we need scheduling, or we can say when we need preemptive scheduling. Now there are four conditions. For situation 1 and 4, there is no choice of scheduling. What was the first condition? When a process switches from running state to waiting state. This was situation 1, and situation 4 is when a process terminates. So for situation 1 and 4, there is no choice in terms of scheduling. A new process, if it exists in the ready queue, must select it for execution. There is a choice, however, for situation 2 and 3. What was situation 2? When a process switches from running state to ready state. And what was situation 3? When a process switches from waiting state to ready state. So there is a choice for situation 2 and situation 3. When scheduling takes place only under circumstances 1 and 4, we say that scheduling scheme is non-preemptive or cooperative. Otherwise, it is preemptive. So under non-preemptive scheduling, once the CPU has been allocated to a process, the process keeps the CPU until it releases the CPU, either by terminating or by switching to the waiting state. This scheduling method was used by Microsoft Windows 3.x. Windows 95 introduced preemptive scheduling, and all subsequent versions of Windows operating system have used preemptive scheduling. The Mac OS operating system for Macintosh also uses preemptive scheduling. Previous version of Macintosh operating system relied on cooperative scheduling. What was cooperative scheduling? Cooperative scheduling is the only method that can be used on certain hardware platforms because it doesn't require the special hardware. What was the special hardware? Say a timer needed for preemptive scheduling. But unfortunately, preemptive scheduling incur a cost associated with a cross to shared idea. Consider the case of two processes that share data. While one is updating the data, it is preempted, so the second process can run. The second process that tries to read the data which are in inconsistent state because process 1 P1 was in the middle of updation. The second process then tries to read the data which was in inconsistent state. In such situation, we need new mechanisms to coordinate access to shared data. Preemption also affects the design of operating system kernel. During the process of a system call, the kernel may be busy with an activity on behalf of a process. Such activities may involve changing important kernel data. What happens if process is preempted in the middle of these changes and the kernel needs to read or modify the same structure? It will create chaos. So we need another different type of scheduling. But before that, we should learn dispatcher. I want to introduce one new term, dispatcher. Another component. This is another component involved in the CPU scheduling function. It is dispatcher. The dispatcher is the module that gives control of the CPU to the process selected by the short-term scheduler. The function involves the following: switching context, switching to user mode, jumping to the proper location in the user program to restart that program. The dispatcher should be as fast as possible since it is invoked during every process switch. The time it takes for the dispatcher to stop one process and start another process is known as dispatch latency. So now there are some scheduling criteria. Whenever CPU scheduling is being done, scheduling criteria is kept in mind. In the slide you can see, in scheduling criteria we need to maximize CPU utilization and throughput and minimize turnaround time, waiting time and response time. We can say that different CPU scheduling algorithms have different property, and the choice of a particular algorithm may favor one class of process over another. In choosing which algorithm to use in a particular situation, we must consider the properties of various algorithms. Many criteria have been suggested for comparing CPU scheduling algorithms. Which characteristics are used for comparison can make a substantial difference. It can make enormous amount of difference in which algorithm is judged as the best. Which one is the best? That needs to be kept in mind. So there are certain criteria which we need to consider while scheduling. What are the criteria? First is CPU utilization. We want the CPU to keep it busy as possible. Conceptually, CPU utilization can range between 0 to 100%. In a real system, it should range from 40% to 90%. Throughput. What is throughput? If the CPU is busy executing processes, the work is being done. One measure of work is the number of processes that are completed per unit. The number of processes that are completed one unit is known as throughput. For long processes, this rate may be 1 process per hour. For short transaction, it may be 10 process per second. Now, next criteria, turnaround time. What is turnaround time? Say we are looking from a point of view of a particular process. The important criteria is how long it takes to execute that process. The interval from the time of submission of a process to time of completion of the process is called turnaround time. I am repeating again, listen carefully. What is turnaround time? The interval from the time of submission of a process to the time of completion of a process is known as turnaround time. Turnaround time is the sum of the periods spent waiting to get into memory, waiting in the ready queue, executing on the CPU, and doing I/O. What is the next criteria? Waiting time. CPU scheduling algorithm does not affect the amount of time during which a process executes or does I/O. It affects only the amount of time that a process spends waiting in the ready queue. Waiting time is the sum of periods spent waiting in the ready queue. Response time. In an interactive system, turnaround time may not be the best criteria. Often, a process can produce some output fairly early and can continue computing new results while previous results are being output to the user. Thus, another source is the time from the submission of request until the first response is being received. And it is very important to keep in mind that it is desirable to maximize CPU utilization and throughput, and to minimize turnaround time, waiting time, and response time. These are the different CPU scheduling types. These are the different CPU scheduling algorithms. FCFS, first come first serve, shortest job first, under shortest job first, there's non-preemptive, then again shortest job first, or SRTF, preemptive, priority, and round robin scheduling. So these are different scheduling types. These are the different scheduling parameters which I have just discussed. CPU burst time, CPU utilization, waiting time, turnaround time, priority, throughput, load time, and response time. Now we will read about preemptive scheduling policies. In preemptive scheduling, server can switch to next request before completing current one. Preemptive request is put back into pending list. Its servicing is resumed when it is scheduled again. A request may be scheduled many times before it is completed. Larger scheduling overheads than with non-preemptive scheduling. Preemptive scheduling policies is used in multi-programming and time-sharing operating system. Actually, based on the condition, types of operating system, types of programming, scheduling policy, whether it is preemptive or non-preemptive, is chosen. So this is to be kept in mind. This is preemptive scheduling policy. Now we come to non-preemptive scheduling. When non-preemptive scheduling is used, when a process terminates or process switches from running to waiting state. In this scheduling, once the resource, what are the resource? CPU cycles. Once the resource is allocated to a process, the process holds the CPU till it gets terminated or it reaches a waiting state. This is a criteria when non-preemptive scheduling is used. These are scheduling criteria I have just discussed. CPU utilization, keep the CPU as busy as possible from 0 to 100%. This is theoretical, but in practical, actually CPU utilization is 90%. Then throughput, it is a process that completes their execution per unit time. Turnaround time, amount of time to execute a particular process. Waiting time, amount of time a process has been waiting in the ready queue. Response time, amount of time it takes from when a request was submitted until the first response is produced. Actually, there are different scheduling algorithms, and we choose scheduling algorithm based on these scheduling criteria. These are optimization criteria. What is the goal? What is our goal? We need to maximize CPU utilization, maximize throughput, and minimize turnaround time, minimum waiting time, minimum response time. These are some CPU scheduling algorithms. CPU scheduling algorithms: first come first serve, shortest job first scheduling, priority scheduling, round robin scheduling, multi-level queue scheduling. These are different. I have kept it in bold because they fall under the different category. Multi-level queue scheduling, multi-level feedback queue scheduling. These are different types of scheduling algorithms. Now we come to first come first serve scheduling algorithm. By far this is one of the simplest CPU scheduling algorithm. With this scheme, the process that requests the CPU first is allocated the CPU first. The implementation of FCFS is easily managed with FIFO queue. Since queue operates on FIFO, so it is easily managed with a FIFO queue. When a process enters the ready queue, its PCB is linked on the tail of the queue. When the CPU is free, it is allocated to the process at the head of the queue. The running process is then removed from the queue. The code for FCFS scheduling is simple to write and understood. But on the negative side, the average waiting time under the FCFS policy is often quite long. So we need to consider one problem: process and burst time. Now suppose there are process P1, P2, P3. If the process say arrive in the order P1, P2, P3 and are served in FCFS order, we get the result shown in the NAT chart, which is a bar chart that illustrates a particular schedule including the start and finish time of each of the participating processes. The waiting time is 0 milliseconds for process P1, 24 milliseconds for process P2, 27 milliseconds for process P3. Thus, the average waiting time is 0 plus 24 plus 27 divided by 3. That comes to 17 millisecond. So what we can see, the average of waiting time in this policy is quite long. But suppose if the processes arrive in the order P2, P3, P1, consider the previous slide which shows if say the processes arrived in the order P2, P3, P1, the results have been different. At that time the average waiting time should be 6 plus 0 plus 3. For process P1 the waiting time would be 6 millisecond. For process P2 it is 0. For process P3 it is 3. So the average comes out to 3 millisecond. This reduction is substantial. Thus the average waiting time under an FCFS policy is generally not minimal and may vary substantially if the process CPU burst times vary greatly. Now we should learn convoy effect. Actually, in addition, consider the performance of FCFS scheduling in a dynamic situation. What is dynamic situation? Assume that we have one CPU bound process and many IO bound processes. Only one CPU bound process is there and several IO bound processes are there. As the process flow around the system, the following scenario may result. The CPU bound process will get and hold the CPU. During this time, all the other processes will finish their IO and will move into the ready queue waiting for the IO. While the processes wait in the ready queue, the IO devices are idle. Eventually, the CPU bound processes finishes its CPU burst and move to an IO device. All the IO bound processes which have short CPU burst execute quickly and move back to the IO queue. At this point, the CPU sits idle. The CPU bind process will then move back to the ready queue and be allocated the CPU. Again, all the IO processes end up waiting in the ready queue until the CPU bound process is done. There is a convoy effect as all other processes wait for one big process to get off the CPU. This effect results in lower CPU and device utilization than might be possible if the shorter process were allowed to go fast. This is one of the disadvantages of FCFS scheduling. But however, FCFS scheduling has some advantages also. What are the advantages? Simple form of this scheduling algorithm, easy to program, intrinsically fair. These are the advantages of FCFS scheduling. What are the disadvantages of FCFS scheduling? Waiting time can be large. It is not suitable for time sharing system. Since for time sharing system it is not very suitable, also waiting time is very large. Thank you for watching. Hope you have gone through FCFS. Hope you will go through the FCFS scheduling and CPU scheduling criteria, and we will discuss the other CPU scheduling algorithm in the next class.